Okay, thank you for that introduction. Can everybody hear me all right? Okay. So today, Adam and I are going to tag team this presentation, and we are going to be talking about anaerobic membrane bioreactors, and we're going to really build on some of the themes that our previous presenters have introduced, talking about resource recovery from domestic wastewater. And so anaerobic membrane bioreactors represent an emerging technology. They haven't been demonstrated at the full scale yet, only at the pilot scale, for energy recovery from domestic wastewater. Before I begin, I'd like to acknowledge my co-authors. There's a large group of University of Michigan students, postdocs, and professors working on this project, and we are collaborating with the Sally Group, Hampton Roads Sanitation District, and Carollo Engineers. So this is a schematic of a conventional wastewater treatment facility. We use clarifiers and aerobic activated sludge process to treat our waste. And there's a number of deficiencies that some of the other presenters have already pointed out with this process from a sustainability perspective. First is that aeration is extremely energy intensive. Like the others, 45 to 60% of energy demands of treatment come from aeration. Second is that with aerobic processes, you produce a significant amount of residuals that need to be managed and handled, and that's often done with anaerobic digesters, which can be used to produce biogas. And then third is that there's a potentially large land requirement, and that's both due to the number of unit processes used here, but also because of the residuals that are produced that need to be disposed of, either by landfill or land application. And so one way that you can implement resource recovery at the treatment plant is to capture that biogas that's being produced using a cogeneration unit to produce heat and electricity. And while we have anaerobic digesters widely implemented, cogeneration is not. Less than 10% of treatment facilities with anaerobic digesters currently use cogeneration, and that's because, as was alluded to before, these are expensive and they have long payback periods. And so one way to enhance energy recovery is to operate your treatment facility to enhance the amount of biogas you produce. And as the last speaker mentioned, you can reduce your sludge age, so use a high-rate activated sludge process, which I'll refer to as HRAS plus AD, where you reduce the hydraulic retention time and solids retention time in your aeration basin. And by doing this, you maximize the amount of sludge you produce that goes to your anaerobic digester, and you increase the amount of biogas that you produce, thereby increasing the amount of energy you can recover, and reduce that payback period. And so this represents a conventional approach, a stepping stone technology to recovering more energy from domestic wastewater. So the other technology that we want to focus on is anaerobic membrane bioreactors. And this is an emerging technology that combines anaerobic treatment, so directly treating wastewater anaerobically, not just the solid side, and combining that with membrane separation. So this is just a picture of a membrane cassette and a close-up of flat sheet membrane that makes up that cassette. And a simple schematic to show how this works: you have these submerged membranes, which is represented by this dotted line. We draw the effluent through the membrane, and the membrane retains the particulate organics and inorganics inside the bioreactor. And when we do that, those organics and inorganics can accumulate on that membrane surface, and that's what we call the foulant layer. And so one thing we do to prevent the membranes from fouling is by bubbling over biogas that's recirculated from the headspace of the bioreactor over the surface of the reactor to dislodge some of that foulant. And as that foulant accumulates, it takes more pressure to draw that effluent through the membrane, and we refer to that as transmembrane pressure. And just a couple other terms that we'll use in this presentation to describe the operation of these membrane systems: flux, which refers to the liquid flow rate per membrane area, and specific gas demand, which refers to the biogas sparging flow rate per membrane area. And then the last thing I want to mention is this dissolved methane that's present in the effluent of an anaerobic membrane bioreactor. So some of the methane that's produced during anaerobic treatment is not recoverable from the headspace of the bioreactor, and that's because it remains dissolved in the liquid phase. And so when the effluent leaves the reactor, it contains a significant amount of dissolved methane, which both represents a lost energy source because we're not recovering it, but also a potential potent greenhouse gas emission, because when it goes out and is discharged into the environment, that methane can be released. And we'll talk about that a little bit more later. So just to go back to our flow diagram, if we think about how an ANMBR might be implemented, it would essentially replace the two clarifiers and the aeration basin, and because we're using membrane separation, we would directly capture that biogas from the ANMBR, use a cogeneration unit, and produce electricity. And this represents a way to enhance energy recovery potentially because we are capturing a greater fraction of the organics present in wastewater because we're directly treating the liquid stream as opposed to just the solid stream, which we do with conventional anaerobic digestion with an activated sludge process. So there's a number of proposed benefits of this technology that need to be validated as it goes to the full scale. And one is that it's a low energy technology because we don't use aeration. Second is that you produce much fewer residuals because it's anaerobic microorganisms that we're using as opposed to aerobic microorganisms. And that leads to a smaller footprint, both because of fewer unit processes and also because there's less residuals to eventually dispose of. So with that introduction of the technology, I'm just going to give a quick outline of our talk. I'm going to present some results from a life cycle comparison, so a system analysis that we use to evaluate anaerobic membrane bioreactors against more conventional technologies like high-rate activated sludge to establish design targets. And then Adam's going to talk about some lab scale work that he's been working on looking at the biological activity in a membrane biofilm and the implications that has on energy use, dissolved methane, and effluent quality. And then we're going to talk about how these two studies are informing some of the ongoing work that we're doing at the pilot scale and at the bench scale, looking at ANMBR treatment. And for anyone who's signed up for the early bird tour tomorrow, you'll have an opportunity to see the ANMBR at the treatment plant. Okay, so to get into our LCA, what we did is we defined our assessment scenarios as the treatment of 5 million gallons per day of domestic wastewater to achieve 30/30 effluent standards. And we did a bunch of different scenarios. We looked at two different wastewater strengths, one which is a medium wastewater strength, which is probably more typical of the US, COD of 430 milligrams per liter, and a higher strength wastewater of 800 milligrams per liter. And this would be, for example, as water conservation efforts go into place or in areas with less precipitation or newer infrastructure, we're going to start to see higher concentrations, higher strength domestic wastewater. And then we used a wastewater temperature of 15 degrees C, and we looked at 3 different sludge disposal scenarios. And to simplify some of our results, we also considered a hypothetical aggregate sludge disposal scenario, which is based on the average US practices for sludge disposal. What we did was we designed our treatment systems and we modeled them using process models. So we did ANMBR and HRS plus AD, but we also included 2 other reference systems, conventional activated sludge with anaerobic digestion and aerobic membrane bioreactor with anaerobic digestion. And we decided to include these because they use the same solids-liquid separation processes as our energy recovery systems, but they're not specifically designed for enhanced energy recovery. Then we did a life cycle inventory where we basically accounted for all the inputs and outputs, both in terms of energy and materials involved in the treatment of 5 million gallons per day of domestic wastewater. And so this is just a list of some of the things we accounted for. Energy demands such as pumping and mixing, also membranes, materials, chemicals for cleaning, and also those direct methane emissions that come from the anaerobic MBR's effluent. From there, we did an impact assessment where we translated those flows into environmental impacts. And these are all the different environmental impact categories that we considered, but today we're just going to focus on the global warming impacts and tell the story that we found with those and how we used those results as well as the energy results from our modeling to interpret and inform some decisions about where anaerobic membrane bioreactors are heading or where they should head, and to set some design targets that need to be evaluated at pilot and full scale. And lastly, we did an uncertainty and sensitivity analysis, and that's because there's a large degree of uncertainty associated with some of the parameters that we used in our model, specifically for the anaerobic membrane bioreactor because it is an emerging technology. And so for each of the parameters that we used in our model, we assigned a possible range of values that they could assume and a distribution based on the likelihood of those values. And then we did Monte Carlo simulations to get an aggregate uncertainty. And I just want to point out that we did 2 different uncertainty analyses for the anaerobic membrane bioreactor. We did an existing uncertainty and a future uncertainty. The existing uncertainty was using parameters, values that were based on how ANMBR is today. So the values that have been reported in the literature for pilot scale systems. Then for the future uncertainty, we assumed parameter values based on where we think ANMBR will go as it goes to the full scale. And we really base these on aerobic membrane bioreactor parameters that have been implemented at the full scale where possible. So getting into our results and starting with energy, here we have a graph with energy on the y-axis, and the bars that are below 0 represent energy recovery, and the bars above are energy demands. So here we can see for the treatment of medium strength wastewater that anaerobic membrane bioreactor recovered more energy than high rate activated sludge, but it also used significantly more energy if you look at the blue bar primarily for membrane sparging or fouling control. So if we look at the net energy, which is those yellow diamonds, we see that high rate activated sludge had net energy recovery, whereas ANMBR did not. If we compare to our reference systems, we see that aerobic membrane bioreactor had the overall worst net energy balance, and that's because it recovered significantly less energy, but it also used a lot of energy both for aeration and for membrane sparging, so fouling control. So if we look now at higher strength wastewater, so this is a COD of 800 milligrams per liter as opposed to 430, we see the story is quite a bit different. For anaerobic membrane bioreactor, I guess I can use this, we see that it recovers significantly more energy, but the energy demands stay relatively constant. And that's because we assume that the energy required for fouling control was independent of wastewater strength. But for high rate activated sludge, it does recover more energy, but it also has more aeration energy demands. And so the result is that anaerobic membrane bioreactor is actually slightly better in terms of its net energy balance than high rate activated sludge for a higher strength domestic wastewater. And then if we look at our 2 reference systems, or the conventional activated sludge and aerobic membrane bioreactor, we see that they are both detrimentally impacted by this increase in wastewater strength. And that's because they use more energy associated with that higher strength wastewater for aeration than the amount they make back in recovery. And so that was our base case scenario for energy, and this is presenting the results of our uncertainty analysis. So looking at the impact of the parameters that we chose on the energy demands. And so here we can see that for the treatment of medium strength wastewater, ANMBR, which is shown in the blue, has a much wider distribution than HRAS plus AD, which all falls into that orange box. And that's because there's a lot more uncertainty associated with ANMBRs as they are emerging. But we also see that it's very unlikely, based on our uncertainty analysis, that ANMBR will recover more energy than HRAS plus AD in its current state. But if we then look at future projecting ANMBR as it evolves, assuming that eventually it gets to have fluxes and specific gas demands closer to what an aerobic membrane bioreactor currently operates at, we see that it's very likely, even for medium strength wastewater, that it will have a better net energy balance as compared to high rate activated sludge. Now if we overlay high strength, so this is the 800 milligram per liter domestic wastewater COD over this, we see that even in its current state, so using parameter values that exist for ANMBR at the pilot scale now, it's very likely that ANMBR, which is this blue, it's very possible that ANMBR will recover more energy than HRAS plus AD. And for high strength wastewater in the future, assuming it evolves as it goes to the full scale, we see that will be the clear choice for energy recovery. So building on some of those energy results, we also wanted to talk about some of the environmental impacts, and we're going to focus on global warming here. And so this is a plot that shows energy on the x-axis and global warming on the y-axis. And what we really want is technologies that get into this green quadrant in the top corner. So technologies that are both energy recovering and carbon offsetting. If we look at these 3 systems here, so high rate activated sludge and our 2 reference systems, we see that there's this relatively linear relationship between energy and global warming impact, which makes sense because basically all of the global warming impacts are due to electrical energy use. But when we overlay anaerobic membrane bioreactor on this, we see that obviously there's a much larger spread. This is the spread from our Monte Carlo simulations and our uncertainty analysis. because it's an emerging technology, but we also see that there are disproportionately greater global warming impacts per energy use. And this is essentially just due to that dissolved methane present in the effluent, which we assume, if it's discharged to the environment, will be released. And so if we project into the future of where ANMBR could go as it goes to the full scale, we'll see that it could approach this linear line between energy and global warming impact, and that's if that dissolved methane is those emissions are mitigated from being released to the environment, and as we improve the energy efficiency of treatment. And so what we really wanted to do with this study was to identify what are the design targets for ANMBR that's going to get it to here, where it is both energy recovering and carbon offsetting, but also competitive with high-rate activated sludge, which represents our conventional technology for energy recovery. And just to give two examples of future scenarios that we think are very realistic for anaerobic membrane bioreactor, if you operate an ANMBR with a biogas sparging flow rate of 0.082, which is what the current design SGD is for an aerobic membrane bioreactor, which is why we think it's very realistic, it will have a comparable net energy balance to high-rate activated sludge. Similarly, if we used intermittent biogas sparging, so instead of constantly sparging these membranes, we instead used on-off, where we only sparge 50% of the time, which is currently being used for aerobic membrane bioreactors now, and we increase the flux slightly from 10 to 15 LMH, we could also see a comparable net energy balance. And so with that, I'm going to hand it over to Adam, and as we reduce the amount we sparge our membranes, it will have impacts on this foulant layer that builds up on the membrane biofilm. So he's going to talk about some of the bench scale work that he's been doing looking into that.
All right, thanks, Lauren. So like she said, part of the motivation for this was building off of the LCA and thinking about reducing those biogas sparging energy demands. And so what we're interested in how that could affect operation of these systems. So if we look at sort of a simplified schematic with the membrane and this foulant layer that Lauren introduced previously, we have biogas sparging here. We know that in some cases, depending on how the anaerobic system's operating, we could have some soluble COD in the reactor, which could be comprised of acetate and propionate. And then we also have dissolved methane, which would likely be at saturation conditions according to Henry's law. So part of our questions were if we were able to develop a biologically active membrane biofilm here as part of that foulant layer, can we improve the effluent quality by removing some of those components such as acetate and propionate? And then also, what does that do to methane? If we produce methane in this biofilm, what's the fate of that methane? Is it going to lead to oversaturation conditions in the permeate and possibly exacerbate those greenhouse gas emissions and also the loss of energy? And then finally, bringing it all back together, what are the impacts of sort of this biologically active biofilm on energy and also global warming emissions? So Sherry presented a similar schematic earlier, so I'll go quickly through this. But in anaerobic treatment, we start with complex organic polymers, and those are fermented until we get to some of our intermediate compounds, such as propionate. And then at the bottom half of the metabolisms here, we have syntrophic propionate oxidizers, for example, that produce acetate, hydrogen, and CO2. Those are ultimately converted into methane and CO2 or biogas by acetoclastic methanogens, and then also hydrogenotrophic methanogens. So as I mentioned in the previous slide, oftentimes when anaerobic systems aren't completely converting organic material to biogas, we wind up with some residual propionate, for instance, or other volatile fatty acids, and then also acetate in the effluent that ideally we'd like to remove and convert to biogas. So if we think back to that original cartoon that Lauren presented, we have this foulant layer, and so we were interested in whether or not we can lead to conditions where we promote active microbes to establish in that foulant layer and remove some of these compounds such as propionate and acetate to improve our effluent quality. So to do that, we conducted experimental work at the bench scale using a small anaerobic membrane bioreactor. We treated a synthetic low-strength wastewater and we operated at a psychrophilic temperature of 15 degrees C. This is a drawing of our reactor system. We have 3 flat sheet membranes here, 1, 2, and 3, and we wanted to operate those under different conditions to promote this active biofilm. So we use biogas sparging flow rate to do so, and so for the membrane housing on the left here, which these each produce their own effluents, I do want to point out. For the one on the left, we operated at a very high biogas barging flow rate to limit any accumulation of foulants on that membrane surface. For the next membrane housing, we operated at a slightly reduced biogas barging flow rate. And then for the third one, we operated at an even lower biogas barging flow rate so that we could have 3 distinct levels of sort of fouling and 3 different developments of the biofilm. So Lauren mentioned that we use transmembrane pressure to evaluate the fouling level of membranes during operation, and we operated under this scheme for about 40 days, and these are the transmembrane pressures that developed on average. So for the no fouling membrane housing, transmembrane pressure stayed right around 0, as we expected because we did not allow accumulation of any foulants on the surface. And then for the low fouling case, we had a transmembrane pressure of about 27 kPa on average, and then for the high fouling case, we had a transmembrane pressure of about 45 kPa. This plot shows the permeate quality during these 40 days. So I'm not going to show that. You can see on the x-axis starting at 100. I'm not going to show the first 100 days of operation, but during that time we had fairly high effluent COD. So the system wasn't performing very well, and a large portion of that effluent COD was propionate and acetate. So you'll see that we start here with concentrations well over 100 milligrams per liter. If you look at the 3 lines I have shown here, in blue the no fouling case, in pink the low fouling case, and then in red the high fouling case, you can see that we start and we immediately saw some differences in effluent quality here. And those really continue to increase in magnitude throughout this 40-day operational period. And you can see at the end for the high fouling case we have about 60 to 80 milligrams per liter difference between that and the no fouling membranes. And also by the end of the operational period, we're able to go from CODs well above 100 to a COD of approximately 20 milligrams per liter in the high fouling case. A good portion of the COD that was removed in the biofilm was propionate, and you can see that I'm also showing now in this case the 3 membrane housings, but I'm also showing concentrations of propionate in the bioreactor itself. And those correlated very well with the no fouling case, as we expected, because there was limited biological activity in that biofilm. But what we observed was about a third of the way through the operational period, we started to see propionate oxidation in the high fouling case, which was evidence of development of a syntrophic propionate oxidizing community in that biofilm. And by the end of the operational period, we were able to achieve concentrations below 5 milligrams per liter of propionate. So what does this have, what implications does this have for methane fate in the system? On this plot, over the same time period, on the y-axis, I'm plotting methane oversaturation. So a value of 1 indicates what we would expect for methane according to Henry's law. So for the no fouling case in blue, we see that that correlates very well. When we have limited or no biological activity in the biofilm, methane concentrations remain where they should. But for the low fouling and the high fouling case, we see considerably higher methane oversaturation. So we're producing methane in the biofilm, and that methane is ultimately leaving in the effluent, which is increasing the amount of methane that we're losing and possibly increasing the amount of greenhouse gas emissions as well. So past this, we had a couple objectives. One was that we wanted to replicate the performance that we had on the high fouling case on the other membrane housings, but we were also interested in how tightly adhered that active biofilm was on the membrane surface. So we're interested in, could we retain that biological treatment in the biofilm, but do so at a lower transmembrane pressure? So to do that, we took our system and we instead operated these first 2 membrane housings, which were no fouling and low fouling, under high fouling conditions. And then on the third one, we increased the biogas barging flow rate so that we could bring transmembrane pressure back to 0. And so we called that our history of high fouling. So this plot shows the timeline for that experiment, and I'm only showing the history of high fouling case here. First, you can see that throughout this operational period, despite having no transmembrane pressure, we were able to achieve the same effluent quality, if not a slight improvement in effluent quality. So really what we found is that active active biofilm is very tightly adhered to the membrane surface and somewhat separate from this foulant layer that develops that leads to higher transmembrane pressures. When we look at the other 2 membrane housings, we found that the effluent quality began to converge by the end of the operational period, and in all cases we're achieving effluent CODs below 30 milligrams per liter. So some of the ongoing work that we're doing, which Lauren briefly mentioned, is a pilot-scale anaerobic membrane bioreactor that some of you will see tomorrow on the tour. And so we want to evaluate different operational strategies for reducing the energy demands using some of the design targets that we established in our life cycle assessment. So our system consists of an anaerobic bioreactor, and then it's connected to 3 different membrane systems. We have hollow fiber membranes, flat sheet membrane system, and then the third is a ceramic disc membrane system, which is somewhat more novel. It actually relies on rotating discs to prevent membrane fouling, so it doesn't use biogas sparging at all. So we think that's a great opportunity for reducing those energy demands. And then last, we also have some lab scale work, which is evaluating downstream nitrogen removal from an anaerobic membrane bioreactor. And we have 2 approaches that we're evaluating, the first being a membrane biofilm reactor. And this is somewhat different than what you normally think about with membrane bioreactors. Instead, we're using a gas permeable membrane, and oxygen, or air, is diffused through the fiber and outside. And then here we would have our anaerobic effluent, which contains, for instance, ammonia, methane, and sulfides. And so this creates a biofilm that grows on the surface of the membrane over a redox gradient so that we can get some of these metabolisms such as nitration and anammox, even potentially anaerobic methane oxidation to occur within that biofilm. And then our third approach is to use a granular system. And in this case, we're also relying on a system that has a redox gradient across the granular, where you'll have an aerobic zone here and then an anaerobic zone in the middle, which could support metabolism such as anammox or anaerobic methane oxidation. So in conclusion, we used a life cycle assessment-based approach to develop design targets for anaerobic membrane bioreactor technology. And then we really found, based on that the energy demands for fouling control and also the dissolved methane need to be mitigated if we want to reduce the global warming emissions for treatment. And then finally, we found that some of these low-energy fouling control strategies could lead to development of a biologically active biofilm in the system, and this could have some implications on both effluent quality and then also on the concentration of dissolved methane in the effluent. So before we answer questions, just some acknowledgements. The Environmental Biotechnology Group, which is Lute Rask and Nancy Love and Krista Wigginton's research group, and then East Lab, which is Steve Skurlis' research group. And then the pilot scale work is in collaboration with HRSD and Carollo and Sally Group, and then funding from WRF, Water Reuse Foundation, and NSF. So thank you.